Cool. Anyway, thanks everyone for coming in person and on the Zoom. We got you. Yeah, so Stratis and I are going to talk to you about energy-based models. I can change the slide. Yes. Okay, so the first question is, what are energy-based models? To answer that, yeah, suppose we have access to some unnormalized probability distribution, P tilde of theta. Obviously, we can just divide that by some normalizing constant Z of theta, and that gives us a normalized probability distribution. And we might care about this because we don't always have access to a nice, well-behaved probability distribution. And we can just call this the negative log of this unnormalized probability distribution our energy function. And yeah, it's equal to the negative log of our normalized probability distribution up to a constant, which is independent of our data. And that constant is just this Z theta, or well, in this case, the negative log of Z theta. And Z theta is also called the partition function. So broadly speaking, energy-based models refer to this class of model where we're dealing with an unnormalized probability distribution, which we can then define this energy function, which is the negative log of the unnormalized distribution. And crucially, the normalizing constant is intractable. So a lot of what we're going to be talking about here is how to deal with that problem of the intractable normalizing constant. But before we get to that, or before I hand over to Stratis, who will start getting into that, let's talk about why we might care about energy-based models. So the first reason is that they bring us a lot of flexibility. And the first way they bring us flexibility is in the model design. So energy-based models, unlike autoregressive models, VAEs, normalizing flows, place very few restrictions or often no restrictions on the kind of model we're using. So we can use arbitrary neural networks. We just need that our energy function be some function which takes in an input and returns a scalar. If we have a function like that, we're golden. So we can use a graph neural network, we can use a transformer, we can use a ResNet, whatever modern neural network we want, basically. And yeah, crucially, we're not constrained to models with tractable likelihoods. The other way that, yes.
That's not quite true, is it? Because you've got to normalize. So,
well,
isn't there going to be a problem if our partition function is infinite?
Yes, so it's not quite true, but we can often, approximate the partition function or avoid calculating the partition function depending on our training method.
But what if the actual partition function is infinite? Like it's not actually normalizable.
So you have, that was the question, right? So
yeah.
You have an arbitrary energy function. That's not quite true. It has to correspond to a normalizable density of distribution.
I think that is true, and it's somewhat, I have to say, I haven't seen in papers, like we're also going to talk about some papers like later on, of course, some examples. A lot of the time they don't refer to that constraint at all, and I think part of the reason why they don't refer to it is that like it turns out to be automatically handled in some cases, in the sense that the methods that we'll be showing try to tackle not having to estimate to write down this Z, and then by training the model using these recipes that don't actually rely on Z, it turns out that maybe it is handled in some cases, but overall it's like it is certainly a constraint that you should keep in mind. But yeah, also it's not clear in the literature how people actually they don't refer to it very explicitly, so it's a little bit boring. Just full disclosure there. Yeah.
Just for what it's worth, I looked at this question a while ago, and the answer I came to is that the people you look at images are represented in a bounded domain, so it's all between 0 and 1. So therefore, the integral you're doing is not over the whole real space; it's just over this domain, and therefore it's always going to be finite.
Yeah.
But that one only works for like images. So
Yeah.
and that's but that's what people seem to use these for.
Yeah, but then there are other constraints, right? They're bounded. The end is bounded, things like that.
Yeah. So there will be like, yeah. I mean, I think in practice, if you're learning, for example, if you're putting a neural network on, well, it has to be. Yes, it has to be bounded. And if you're learning a neural network on a sort of bounded domain, I'm assuming that maybe it in practice it turns out that this constraint is satisfied as well. So like it doesn't explode off to, in a finite domain. Your neural network does not go to infinity. So
I agree.
but yeah. Yeah, definitely. Yeah, so it's not quite an arbitrary E of theta, and there are more constraints, but yeah. It would be great if also the literature referred to this more, but yeah, we'll see more of that later as well.
Cool, thanks for the questions. Yeah, so in addition to an almost very flexible model design, EBMs give us a lot of flexibility in the kinds of problems we're solving. As you know, the same story, basically, if we can rephrase our problem as some function that returns a scalar, you can apply an EBM. So you can, rephrase many things this way. Image classification, bounding box detection, pixel-wise classification, part of speech tagging, image restoration. All of these are examples where we take some inputs and return a scalar, which is, going to be a score that says, how well does X match? How well does Y match our input X? Obviously, in these examples, the tricky part is actually, in many cases, inferring the Y that best matches X. And that's really where the sort of the problem of energy-based models comes in, is doing this inference. And so what we're going to be looking at is ways of doing inference in these models in a tractable and efficient manner. And with that, I'll hand over to Stratis, and he'll tell us a bit about the origins, the origin story.
So yeah, so we've separated this presentation into two bits. One talks about the sort of older, sort of the first kind of EBMs that were introduced, and then we'll talk about more modern approaches. So let's see. Okay, cool. So arguably one of the first successful examples of training EBMs was by Hinton, where he talked about a particular class of EBM, which is the product of experts. So a product of n experts has the following form. So it is, you take n tractable distributions, pick your favorite models, and then you product them together. So and then you normalize them by z theta up front. So what this model says, essentially, it's a form of and function. So each of the experts gives an opinion on a particular data point, like how likely do you think this data point is? And then you aggregate the experts, product them together, and by producting them, you're essentially doing an and operation. And then you normalize up front with the z theta. Now, even though the n experts might be tractable individually, they're normalized by producting them. You might end up with something that is not, you will end up with something that is not normalized. And in fact, z theta might not even be available in closed form. So this is just taking logs, we just re-express this for clarity in terms of the energy function and the partition function that we showed earlier on. So what we would like ideally to do is to train the model via maximum likelihood. But unfortunately, that's not possible because you can see in the objective. Do you see my cursor? Okay, yeah, perfect. Yeah, in the, well, if we just plug the equation 4 into 5, then you see that because log of z of theta is intractable, you can't do the argmax. You can't even take gradients tractably through it. So in particular, if you take gradients, you end up with these expressions. So we just took the gradient of equation. So we just took the gradient of the log probability in equation 6, and we got these two terms. The first term is just the negative energy, and this is in fact that should be the gradient of the negative energy. Sorry about that. That's a typo. And then you get the gradient of the log partition function. And if we write this out further, we get that this second term, the gradient of the log partition function, is equal to this expectation. And the term in the expectation is tractably evaluated because it's just the gradient of the energy function, which is stated here. But unfortunately, we need to sample from the model distribution P of theta. And that is just, well, you could say just as intractable as integrating the normalizing constant in a sense, because it amounts to doing Monte Carlo over an arbitrary, using an arbitrary, drawing samples from an arbitrary distribution, and doing that in CMC can be quite hard. So yeah, drawing these samples is intractable in general. So what Hinton suggested is contrastive divergence, what he proposed. So contrastive divergence, as we'll see, is a cancellation trick plus an approximation. Let's give two definitions first. So let's write P0 for reasons that will become clear later. Let's write the data distribution PD as P0, and it will be clear why we do this in a second. So, and also note that doing maximum likelihood is equivalent to minimizing the KL divergence between the data distribution P0 and the model distribution P theta. So that's just a quick rearrangement. And now the second definition is let's define what we'll call a contrastive distribution P of T of X, which is defined as follows. So first, so this will be a distribution that is implicit in the sense that it's implied by a Markov chain. So we'll set up a Markov chain in the following way. We'll sample an initial point X0 from P0. That is our data distribution. And then we'll set up a Markov chain, pick your favorite MCMC method, Langevin dynamics, Gibbs sampling, Metropolis Hastings, anything you might like, but it has to be a valid MCMC method. With target distribution P theta. So that's the distribution implied by your model. So you set that up, and then you draw a sample from this Markov chain by integrating or by simulating this chain for T steps, where T is a fixed number that you choose at the beginning of your train. And that defines the distribution PT. So PT is just, if you imagine evolving your Markov chain, PT is the marginal distribution of the samples of this Markov chain at step T. And this is relatively straightforward to simulate for T steps. It's not so hard. And note that because of the way we set up the Markov chain, PT converges to P theta, which is, as T tends to infinity. And so the stationary distribution P infinity theta is equal to P theta. So this is just some bookkeeping that we do at the start to define what is happening. And now the idea is to run MCMC for a few iterations, typically maybe even one iteration. And instead of minimizing the KL divergence that is equivalent to doing maximum likelihood, we'll minimize the KL divergence between the data distribution and the stationary or model distribution, minus the KL divergence of this implicit distribution PT to the data distribution or stationary distribution to the model or stationary distribution. Note that P infinity and P theta are the same by construction. Right. So what is the motivation? The motivation really under the hood is the fact that there is the annoying term that comes from Z theta cancels. But there's also some intuition about why this scheme makes sense. So before looking at the cancellation and why you can actually, why this objective is more tractable than just maximum likelihood, let's look at some intuition. So the objective has two terms. So the first term is just the KL divergence between data and stationary distribution. And the second KL is between the contrastive distribution and the model distribution. So the first property is that PT, by virtue of running Monte Carlo, is always closer to the stationary distribution than the initial distribution. So intuitively, if you start at time 0 and run your Markov chain, at any point downstream, you'll be closer to the stationary distribution than what you started out with initially. And that means that the first term is always greater than the second term, which means that this objective is always positive or non-negative. The second property is that if P0 is equal, so if the data distribution is equal to the stationary or model distribution, so will be PT, because you start from P0, and if P0 is equal to P infinity, then your Markov chain just makes no changes to this distribution over time. And so if this condition is true, then we have that the difference in KLs here is 0. And so this objective is kind of nice, like a KL. So it's always non-negative, and it is 0 when you have P0 equal to P infinity. And the other property that is kind of nice for intuition is that running T to infinity recovers maximum likelihood, because if we run T to infinity, then the second KL becomes 0 and we recover maximum likelihood. So, and that's this property again in an equation. So the intuition here is that this new objective encourages P infinity, the stationary or model distribution, to be close to the data distribution, and PT to be far from P0. You see the second condition comes from the second term, and you basically want this scale to be large, right? So you want PT to be far from P0, and the reason for that is that since PT starts at P0, the term 2 encourages the chain not to wander away from P0. Okay, and now, the next slide will be a bunch of maths which you don't have to pay attention to or remember, but we've included it because sorry.
Andrew just asked a question. It's probably on the slide. Property 1 is a theorem or intuitive guess.
Okay, so I was thinking about the same thing. So there is a really cool paper by Thomas Cover, which shows precise conditions under which running a Markov chain, or rather any process, stochastic or not, gives you this property. So it turns out that for this, if you set up it turns out that with it is a theorem. So under some conditions, it is a theorem. I can point you to the paper. So in fact, what is cool about this is that this is true for any T. So the KL divergence starts at something high, at P0, and it goes down to 0 in a non-increasing way. So it goes monotonically down. So it's a theorem, and there's a really cool paper that proves this.
So just quickly to clarify, so then so this property is not necessarily true for any Markov chain.
I think if I recall from that paper from Thomas Cover, I think the condition is if you have a Markov chain under some constraints of the Markov chain, this is true.
And the constraints are very mild.
Yeah, the constraints are, I would say, fairly mild.
Okay.
Yeah.
Okay.
I mean, obviously, you'd have your chain would have to be ergodic. So so it will have to be ergodic. So if it doesn't mix, then of course you will never, I mean, actually, this might be true even for chains that that don't mix, but the KL would not go to 0 necessarily. But I can point you to the paper for the exact conditions. It's really, really cool, and I would certainly read it. So this is going to be a bunch of maths showing the cancellation. So if you take a gradient of this objective with respect to theta, you get these 4 terms. The first is identically 0, and then you get 3 more terms, which I'm not gonna necessarily, I'm not gonna go into now to all of them, but I'm just going to give you the maths because it was reasonably it wasn't in the original paper, and it wasn't in any subsequent papers either that I saw. So I thought it would be good to like, yeah, include them here. And if you step through these steps, you get a cancellation of the z theta term. You basically substitute equations 17 and 18 into 16, and then 19 into 17 and 18 as well, and the z term cancels. You don't have to remember any of this, but if you're interested, you can go through the derivation. And this cancellation basically leaves us with this objective. Okay, so this objective contains three terms: green, blue, and black, and the first term can be estimated by setting x equal to the data. So this is the data distribution, and this is a gradient that is tractable to evaluate. So we can estimate this, the first term in the integral. The second term can be estimated with simple Monte Carlo by running your MCMC forward. And then again, the second term is again tractable. So you can draw from this distribution basically. The last term, however, is pretty difficult still. And Hinton ignores it. And so that leaves us with this update rule, or this approximation. And we're going to give more intuition on this in a minute. So by ignoring this term, what essentially is happening, and this is not necessarily the easiest thing to spot, but what is essentially happening, if you look at this later, is that you're basically ignoring how the Markov chain, the implicit Markov chain changes because of your change in parameters. So if you look at this later, I think this intuition would make sense, but it's not necessarily easy to spot straight away.
So is it fair to say that at the end of the day, what we get from this is we just replace the objective, which has an expectation of exact samples, an expectation for approximate samples?
Exactly. Yeah. Thanks. Yeah. Exactly. That's a great intuition. And like, so you basically, although you could have estimated the original objective using exact samples from a really long Markov chain, which you would wait to like really long times to get mixing, you can instead run a Markov chain for a little bit of time and then compare your data samples and your contrastive samples from this Markov chain together. And by comparing, we mean taking this difference. So there's no samples drawn here that involve a Markov chain that runs to infinity. They're all like, you know, for a fairly like moderately small number of steps. And also Hinton empirically shows for some admittedly fairly small models that are actually in some sense tractable. He shows that ignoring this term is benign in a way, because he shows that using this update rule also reduces the term that he ignores. So it's a little bit, I think, in a limited domain, he shows that it's relatively benign to ignore the last term. So let's look at restricted Boltzmann machines and how we can do this for RBMs. And so a restricted Boltzmann machine is a model that consists of binary variables. Some of them are visible. These are the X's here, and some of them are hidden or latent. These are the H's, and they're related. Their energy is related via a linear model, which involves weights and biases. So every single one of these variables is connected to another one via a weight, and it also has its own private bias. And the observed data are the X's again, and the H's are hidden or latent. And the difference between the Boltzmann machine and a restricted Boltzmann machine is that in a Boltzmann machine, all the nodes are connected. Whereas in a restricted Boltzmann machine, you don't have the gray nodes. So you don't have you don't have visible to visible or hidden to hidden connections. And we'll see how that actually makes this model really neat to work with contrastive divergence. So for such a model, Z is analytic, but still computationally intractable because you have exponentially many states. The states are variable, are binary. And so you have 2 to the whatever the number of the total number of variables is states. So that's analytic but intractable to compute in closed form for any moderately large model. And so Freund and Hustler pointed out that RBMs, so restricted Boltzmann machines, if you ignore the gray stuff, are products of experts, because given the data, the probability of given a data point, the probability of the data point factorizes over the different latent variables. Now, this is still intractable to compute Z theta in closed form, but it works really nicely with contrastive divergence, and in particular with this Markov chain procedure that we discussed. And so let's look at, so the first term in the contrastive divergence update rule is tractable and nice, so we're not going to talk about it. So we're going to talk about the difficult or more difficult second term. So the way to draw samples from this distribution PT to estimate this quantity is we first sample a data point, x0 from the data distribution. And then we draw H1, so the we draw the hidden variables conditioned on that data sample. And then we flip around and, the point is that it's easy to sample from P of X given H and from P of H given X for restricted Boltzmann machines, because there's no self-connections between the visible layer, the visible variables and the hidden variables. So by conditioning on and alternating between the two layers, it's completely tractable to sample from each layer. So we then flip around and we sample X, like the visible layers X1, first step of the Markov chain, given H1, and then we keep going like that. And so this is a form of Gibbs sampling, where sampling from the conditionals is basically tractable because of the RBM architecture. So you can train this model in this way, and we can show some results. So in the top row, you have some MNIST digits that are unseen by the model, and in the bottom row, we show it shows the result of running this Markov chain on those digits. And basically the thing to take away from this figure is that the model has learned to not wander away from good samples, points of low energy. And in the second plot, I'm not really going to go through it, is that basically it says that even though what the RBM gives you, it doesn't give you a normalized distribution, but rather only unnormalized energy of your data point. That unnormalized energy is still useful for classifying points. So you can use an RBM to get the energies of your various data points, and then use a linear classifier to classify them. So what you should note is that the red and blue stuff here is linearly separable. And then lastly, you can extend this to deep Boltzmann machines by stacking several of these RBM layers together. Surprisingly, I had never looked into this. I had never looked into this before. And surprisingly, the results you get from using these fairly, so this was 2008, and I should have put a reference here, but using these fairly simple and small models, you get pretty good results on both MNIST, but also not so trivial, less trivial data sets like NORB. And so that was a bit surprising that these models can perform so well, even though they're kind of early in the chronological order of models in machine learning. Great. So the summary of the picture so far is that EBMs are a model class with intractable log likelihoods. We can train them by contrastive divergence, which works by setting up a Markov chain for PT, minimizing the KL divergence or an approximate form thereof, the difference between KL divergences rather. The motivation for this is that you get cancellation of the intractable Z term, the partition function. And MCMC is particularly easy for POEs because of conditional independence. And so two questions that we'll be answering in the remainder of the presentation is, can we leverage recent developments in deep learning for training, for combining basically deep models with energy-based models? And are there alternatives for training EBM, so alternative methods other than contrastive diversion? So I'm gonna hand over to James to take us back to more modern approaches for training.
Right, yeah, thanks, Stratis. So I'm just going to quickly recap a little bit of contrastive divergence, give a little bit more details in sort of modern setting, and then we'll get on to more interesting things. So the summary is we want to maximize the likelihood. We can't because of this annoying normalizing constant, but it turns out we can do some tricks and we can compute the gradient of the log likelihood, as shown in equation 24 there. Of course, you know, here we have this, we still have a annoying partition function, the normalizing constant. But it turns out, and I'm afraid I don't have the derivation here, that this annoying gradient can be approximated with a simple Monte Carlo estimator. And there's a reference at the end which has the derivation for this. And basically what this means is that we're taking gradients in this direction, which is the difference between the gradient of our energy function evaluated at our training data and the energy function evaluated at samples from our model, which might seem like a slightly weird direction to walk in. So a little bit of intuition is given in this figure. And basically the idea is we're going to start off with some, untrained model.
I don't understand. We're gonna start
Siri. Sorry, Siri. Funnily, that also happened when I was practicing, I think on the slide as well. Anyways, where was I? Okay, so we start off with some untrained model. And in this untrained model, our training data might have a high energy and random, poor samples from, again, a bad model will have low energy. And basically taking steps in this gradient direction, the difference between the gradient that evaluated our training data and the gradient evaluated our samples, pushes the energy function more to what's shown on the right here, which is a situation where the training data has low energy and our samples, our somewhat bad samples at the start of training, have comparatively worse energy. Now, of course, as training progresses, we also hope that the energy for our samples will get lower and start to get close to the training data. But this is sort of the general intuition for taking steps in these direction. As Stratis mentioned, actually sampling from our model is non-trivial, and so we have to resort to further approximation. And basically, it seems like the literature at the moment has decided that Langevin MCMC is the way to go. At least, basically every paper that I read in preparation for this talk uses some sort of Langevin. So the idea here is we take some of our original training data and we iteratively perturb those training examples with a bit of noise and a little bit of gradient. And as we perturb, we get closer and closer to samples from our actual model. Here, there's one thing to note, which is that this the score function, the gradient of our model, is actually really easy to evaluate in the case of an energy-based model. As I show here, it's basically just the negative gradient of the energy function. So that works out quite nicely. But hold on. What I just showed you, I introduced as being an approximation to the gradient of the log likelihood, and it is, but where Stratis came from was talking about this delta between these KLs, which is quite nicely motivated. And hold on a second. I think something's gone wrong here. Okay. So something has gone wrong here with the slides. Apologies for that. Shouldn't be a disaster though, because Stratis did cover this. Basically, this sort of objective over here, which you can view as an approximation to the gradient of the score function of the log likelihood, rather, is missing a term. And if we actually take the gradient with respect to this this delta and KLs, there's this third term that Stratis mentioned, and it turns out that, you know, well, Hinton said it's okay to ignore this term, but it turns out that ignoring this term, you know, can actually cause some problems. For one thing, there's a paper which should have shown up with a reference there, which tells us that, you know, in certain cases, we actually get sort of degenerate behavior where our updates are cyclical and we don't actually make any progress. And furthermore, Du et al. Show that if you do actually take the effort to approximate this term, you get much more stable training. And what they also show is that including this term is equivalent to an additional term in the loss, which is shown here in equation 30. And yeah, so this loss term is sort of an approximation to including this missing KL term from our objective. And it, you know, as you might have guessed, there's a reason Hinton and basically everyone since Hinton has ignored this term, and that's that it's quite a pain to estimate. So I'm not going to go into the details of how it's actually estimated, but I'll just run you through like a brief summary. So the loss has these two terms. The first is just the mean of our samples. And this we can estimate using MCMC, again, usually Langemann dynamics, but then we have to differentiate through that. And differentiating through a whole MCMC chain is quite expensive. So typically what people do, or at least what Du et al. Do, is they only differentiate through the last update step to keep this somewhat computationally tractable. And the other thing we have to do is estimate this entropy term, the term 2 in our loss. And Du et al. Estimate this with a nearest neighbors approximation, which they note doesn't really work in high dimensions. It works fine in low dimensions, but in the problems we actually care about, it doesn't work so well. But they say, okay, I mean, as long as it's providing some sort of entropy, some sort of regularization, the nearest neighbors is sort of close enough, and they call it a day at the nearest neighbors and get reasonable results. But I think, yeah, there's definitely, probably some more work that will happen here at some point to, come up with a better way to estimate that in a sort of tractable manner. So that's, that's this extra term and this extra KL loss, but, what is this actually doing? Why are we backpropagating through a sum of the, mean of our samples and this entropy term? So this figure sort of tries to explain a little bit of the intuition behind that. So on the top, what we're showing is an energy function. And what we're seeing is, as before, when we have a sample from our model, we want to push the energy for that sample up. And when we have a sample from our real data, we want to push the energy for that down. But when you do that, you can fall into some pathologies. So we could, for example, just learn a model that samples really bad images all the time, or samples the same really bad image all the time. And what this KL loss term is doing is it's preventing those sorts of pathologies. So it's forcing the samples to actually be quite good, to have low energy, and also to be diverse so that we don't just pick the same bad sample over and over again. That's the sort of intuition behind it. There's a ton more detail in the paper, and indeed a number of additional tricks they do. But ultimately, they do get some quite cool results. And I chose this, this figure from their paper for two reasons. One, because the faces here look quite reasonable. There's definitely some artifacts. They're not perfect, but they're definitely faces. And two, because this highlights the sort of product of experts acting as an and behavior that Stratis mentioned. So what they actually did here is they trained 4 conditionally independent energy-based models, conditioning on attributes of the faces, such as young, female, smiling, and wavy hair. And what you can see is that when you compose these conditional energy-based models, we get this and behavior. So the top row is just young faces, the next row is young and female, the next is young and female and smiling, etc. And it works quite well. So I thought that's quite a nice example of this and behavior that Stratis mentioned. Okay, that's sort of the end of today's story with contrastive divergence, at least. But let's move on to some other approaches. The first of which is called score matching. And as you might guess from the name, this has to do with matching score functions. In other words, matching the first derivatives of our functions. Now, why do we care about score matching? Well, it turns out that if you have 2 functions, f and g, and they have the same first derivative, i.e. the same score function, then we know that those 2 functions are equal to each other up to some constant. If we additionally know that f and g are log PDFs, then the constant goes away and these 2 functions are equal to each other. So what how do we say this name? What Proverinen and Dayan do is they propose that we can learn EBMs by minimizing what's called the Fisher divergence. And the Fisher divergence is basically just a metric of the difference between 2 score functions. Do we have an additional question?
Rich.
Cool. Thanks, Rich. Okay, so we want to use this Fisher divergence to learn our energy-based models, but there's a problem here. The problem is this term over here, which requires us calculating the score of our true data distribution, which we obviously don't have access to.
So what is that norm? Is it L2 norm between 2 functions?
It's the L2 norm.
Or is it just one evaluated at X?
Exactly.
Okay.
Yes. Cool. So the problem here is this term here, which we can't actually calculate. But otherwise, everything's nice. So, we can, the rest of this could be estimated with a simple MC estimator. This other term over here is, as I mentioned before, just the negative score of the energy. But yeah, we've got this problem that we can't actually calculate the score of our true data distribution. Luckily, we can use integration by parts, and this again is shown by Proverinen and Dayan. And yeah, using integration by parts, we can actually rewrite the Fisher divergence in a way that it doesn't depend on this intractable term. But this brings in a new problem. And the new problem is this term over here, which requires second order gradients, which we know are quite expensive to compute. And so the sort of big O notation cost for this, for calculating this is d squared, where d is the dimensionality of our data, which again, for real problems that we care about, is probably a bit too expensive. So we move on. We move on to something called denoising score matching. And denoising score matching actually solves 2 problems. One of which I didn't mention before, which is that score matching only works for well-behaved data distributions. In particular, the data distribution has to be continuously differentiable and finite everywhere. And then, as I mentioned, it solves the problem of the computation of these expensive second order gradients.
Just a quick clarification.
Yes.
So the data distribution in here is actually slightly different from the P0 data distribution we found earlier, just for clarity. Like the original data distribution was Stratis, was the empirical distribution of the data, which is like a series of deltas of the.
Yes, yes.
This is like the true general
Yes.
distribution, which is of course the thing you're trying to estimate in the first place. So
Exactly.
in a way, it's a bit sort of back to front. You need that, or you need gradients in that to estimate your model.
Exactly. Okay, so for those listening in who maybe didn't hear that, to clarify, what we mean by P data here is the true data distribution, which we clearly don't have access to. That's what we're estimating, not the sort of series of deltas at observed data, which is the P0 that Stratis was talking about earlier. Thanks, Rich. Yes, so problem one of needing to have a well-behaved data distribution can be solved by just adding a little bit of noise to our data. And this ends up giving us some noise data distribution, which is well-behaved enough, at least, as long as the noise distribution itself is well-behaved. So if we have a nice, continuous, smooth noise distribution, that means that our noisy data distribution will be well-behaved enough for score matching to work. Problem two can then be solved using this noisy data distribution. So Vincent shows that if we, instead of calculating the Fisher between the true data distribution and our model, instead we use the noisy data distribution in our model, we get an expression that looks like this in equation 33. And this is great because you'll note that equation 33 doesn't have any second order gradient terms. So you might be thinking, yay, we're done. The end of the talk, this is how you train energy-based models. Unfortunately, there's some new problems here. The first of which I mentioned second, confusingly, is that this is inconsistent, right? We're no longer learning the true data distribution. We're learning a noisy data distribution. And we don't really care about the noisy data distribution. We want the true data distribution. So ultimately, what we then want to do is have a small amount of noise added. We want a slightly noisy data distribution. The less noisy, the better. Unfortunately, there's a trade-off between the size of the noise and the variance of our estimator. The smaller that noise term, the higher the variance is, confusingly. Now, this can be solved using techniques like control variates, but ultimately it's a little bit dissatisfying that we have to add noise to, a distribution that we don't want to. I mean, sometimes this is fine. For example, if you're learning a discrete distribution, it's sort of unavoidable that we're going to add noise, and so then often, denoising score matching is a reasonable thing to do. But in the case of, us having a already well-behaved, continuously differentiable, finite everywhere distribution, we really don't want to be messing with it by adding noise. So another approach to score matching is called sliced score matching. And in sliced score matching, we avoid these problems of adding noise. And luckily, we also avoid the computational complexity problem, which I'll explain in a moment. But the brief idea behind sliced score matching is, yes, using the slice-Fisher divergence. And what the slice-Fisher divergence is doing is it's taking random projections of our score functions. So we're projecting those onto scalars and then taking the difference between those scalars. So here we need some distribution over the projection distributions. And the only requirement here, as far as I'm aware, is that if we take the outer product of two projection vectors in expectation, that should be a positive definite matrix. So for example, a normal distribution works perfectly well here. That's a common choice. Now, as before, with the sort of standard score matching approach, it turns out we can use the chain rule to avoid the annoying, annoying p data term. And this looks quite similar probably to the result we had before. So you might be thinking, are we not going to run into the same problems of a computationally and, very expensive approach? The key difference here, though, is that this isn't we're no longer dealing with second order derivatives. We're dealing with, products of first order derivatives, or, two applications of the first order derivative. And it turns out that this term over here can be rewritten as this term over here in equation 35. And the key thing to note is that the bracketed term for a given index I is a constant. And so what this means is that the computational complexity is now order of D rather than order of D squared. And so slice score matching is actually quite computationally efficient, and again avoids the noise issue from before. So this, I guess, is sort of the most state-of-the-art score matching approach at the moment. The only other thing to mention very briefly before I move on from score matching is that there are connections between energy-based models trained with score matching and score-based generative models, which are quite interesting and worth reading into if that interests you. Yes.
I had a quick question about the slice score matching.
Yes.
So, I can see that every step of the algorithm is now computationally less expensive. But one worry I have is that in order to train the model, you need to have good coverage of all of this gradient matching across the space. And so that's going to involve sampling lots of these to make sure we've got coverage everywhere essentially. And so do you end up just trading complexity of one of your gradient steps within the optimization process with the number of steps you have to take to train the things that by the end of the day? Do they talk about that or?
Yeah, so there is definitely a trade-off there. So the question there was, are we not just trading off having to take many samples in order to get good coverage in our sliced Fisher divergence with the sort of d squared complexity from before? It definitely is a trade-off, but I think for large enough dimensionalities of our data, it quickly becomes like totally infeasible to do standard score matching. And it's going to be expensive here because, as you say, you do have to get good coverage, but it is actually computationally feasible to do it.
But do they, if they're doing this for images, I guess one of the logical things to do would be to concentrate like sampling massive POV over statistics that are important for images, like edge filters or more complicated things like that. Is that what they end up doing in practice? So you're very smart about the statistics that you project down onto them?
So I'm not super familiar with this part of the literature. I got the impression that there were various approaches for trying to make the sampling more efficient. I'm afraid I can't tell you specifically what they were doing, but there definitely was there was some work on this problem. Is that a chat?
Yeah, Tor has asked a question. Says, could you maximize the V instead of taking extirpation with respect to V?
Okay.
I think that's a sensible thing to do that ends up causing another problem, which it finds directions where you're most mismatched at the moment. So in a way, you want to find the V which maximizes the score. So you find the most mismatched statistic, and then you mix that bit up. And then the problem is just by random sampling, you end up with some statistics mismatched, others not. And you end up focusing on stuff that comes out the tails of the sampling distribution rather than actual statistics that match. We tried a similar approach to that.
Okay. So yeah, for those who couldn't hear, Rich says doing that sounds like a sensible idea, but ultimately ends up giving you other problems, and it's something that they actually tried in a similar setting and it didn't work at all. So yeah, there you go. Thanks, Rich. Cool. So with that, I'm going to hand back over to Stratis to talk about another modern approach.
Thanks, James. So just to think this will be the last bit of it, so hang in there. So there's a couple more interesting training methods for EBMs out there, and there is a very interesting piece of work that relates those with contrastive divergence and gives a lot of intuition about how they work. So yeah, so here it is. So again, Hyvarinen introduced a yet alternative training method for EBMs called noise contrastive estimation. And I think this is quite remarkable, actually. So we start by defining a tractable reference distribution, and by tractable, I mean we can sample from it, we can evaluate it, it's normalized, it's tractable. And then, remarkably, Goodman and Hyvarinen say treat Z theta as a trainable variable. So let's not force the model to be normalized, but let's just substitute a C, a trainable constant C in there. And now we will draw X from either the reference distribution or the data distribution, denoted 0 and 1 respectively. So we'll say 0 if it came from the reference and 1 if it came from the data. And we'll set up a classifier using our EBM. So we'll put an EBM into a classifier. Basically, it's a classifier which comes out of base rule to distinguish between these two events, 0 and 1. So we'll present our EBM and our reference distribution with a sample we just drew, and we'll evaluate the probability that it came from the reference or it came from or that it came from the model. And these are the expressions you get from base rule. Yeah, and when 0 and 1 mean these events respectively. And then, so we'll do that a bunch of times. So we'll draw n samples from the reference, so n samples from the data, and we'll minimize the binary cross entropy. And trying to classify between, did the sample come from the data or from the reference? And remarkably, even though you don't constrain C to be a proper normalized constant, the model does normalize. It turns out that kind of everything is fine. So in particular, Goodman and Hyvärinen showed that if there exists theta star such that our model with those parameters theta star is equal to the data distribution, in other words, if the data distribution is in our hypothesis class, then in the limit of infinite data, we converge to the true optimal parameters, and the true optimal parameters are the unique global optimum. So there is a single extremum, a single optimum, and it is unique. So there's no other maximum. There's no like ambiguity in what the parameters are. And so it's remarkable in a sense that this objective, this training scheme automatically takes care of Z theta. But you can get some intuition as to why that happens if you look at the classification probabilities. So the trainable variable C cannot go to neither negative infinity nor to infinity, because if either of these things happened, then it would completely misclassify either the reference data or the true data. So in particular, if we didn't train via this scheme and we just tried to do maximum likelihood and using this C trainable variable, then you can imagine that if we send C to infinity, then we're going to give the data like infinite probability, and that wouldn't work. But under this particular training scheme, if you let C go to infinity, then that means that you like the right hand side term will always win over the left hand side. So you will always misclassify the samples which came from the reference distribution, and vice versa. So C cannot be too ill-behaved, and that's some intuition as to why you converge to the true Z theta as you train. Now, one issue with noise contrastive estimation is how do you choose the reference distribution P of R? And it turns out that different choices for P of R give massively different results. So originally, Hyvärinen used a Gaussian distribution, but you can imagine that always when you hear Gaussian, you should be a little bit wary of limitations. So this other paper by Salen and Goodman proposed the following reference distribution. So they say this is actually quite similar to denoising score matching in a sense. So you take your data distribution and you perturb it a little bit by some noise, some possibly Gaussian noise. And you set up a similar classification problem where you're trying to, so you do the following thing, you sample an X from your data, and then you perturb that by an amount, by some random noise. And then you present these things to your EBM, and you ask the question, which one came from the true data and which one came from the perturbed version. So this is the classifier you get out of this under this definition. And the typical choice for Q is small Gaussian noise again, but the important thing to note is that you start from the data and then you perturb that a little bit instead of just starting with Gaussian noise. And another observation, so an observation is that equation 40 is invariant to scaling P of theta. So Z theta cancels. So that's another, like that's more intuition as to why this is tractable to do. And yeah, similarly to NC, to noise contrastive estimation, we set up a classification task and we minimize the negative log likelihood under our classifier. In other words, training the classifier to correctly distinguish between which sample came from the true data and which was perturbed. Yeah.
Maybe a bit of context and some questions here. So choosing the reference distribution is really important because if the reference is really, really far away from the data distribution, the classification problem is really easy.
Yeah.
And you get no gradients back.
Yeah.
Pretty much for your model, and so your model just stays where it is because it's already perfectly classified.
Yeah.
That doesn't really converge to the true distribution in equal time. So you need to choose a reference distribution which is close to the true data distribution to make things possible to learn your classifier from it. So I didn't understand. So the idea behind this in general is to use something very much like a kernel density estimate, where essentially you're taking the data and converting that to a kernel density estimate. You've got a Gaussian bump at the data point. That's the Gaussian distribution here, and using that as your reference. That will be quite close to the data, so the model will have to try and fight really hard to tell the difference between fake data that comes from your kernel density estimate and the real data. Now, and then you get to a gradient spectrum to learn a really good model. I didn't understand 40. Shouldn't 40 have the reference model in there somewhere?
Oh yeah. Okay. So you're trying to, I think actually that might be a typo.
I think one of the ones on the bottom.
Yeah, exactly.
Although it looks like you're transitioning.
But the thing, yes. Right. So the point is you're I'll have to double check this, but so that expression I took from a later I took from a later paper that we'll cover in a sec, but you should still be able to evaluate the D in closed form, right? And if it truly was, there's some. All I'm saying is that it probably can't be, PD can't appear in the denominator because otherwise you wouldn't be able to evaluate D in closed form. So the point is. So the two events that the classifier is trying to classify is you draw an X from the data distribution, and then you perturb that by some amount of noise. And your classifier is trying to classify which was the noisy version over the non-noisy version. But I'll have to double check this. But okay, please don't take this. Verbatim. It might actually, now that I was thinking about this earlier today, and I think that I convinced myself earlier, but now I'm not 100% sure that this expression is correct.
One of the X or the X primes comes from ER. That's the
Yes. So the point you just said about Rich about the classification being easy or not is illustrated here. So on the left hand side you have the true data distribution. Sorry.
I was just thinking maybe it is correct. If you know that exactly one of X is a real data point and one is a fake data point, then I think the probabilities work out. So it's either that X is the real data point and then X prime is the modified version, or X prime is the real data point and X is the modified version.
Yeah.
And then I think the denominator would make sense there. determinant. right?
Yeah,
Yeah, so one of X is the real data and X prime is from the R.
yeah, okay,
Yeah.
yeah. Now it makes sense. Now you convinced me. Sorry. Yeah. So yeah, a lot of details, and it's easy to get lost. Sorry. So yeah. So okay. So here's the intuition of like what's happening between NC and CNC. So on the left-hand side, we have the data distribution, the true data distribution, like a dummy model. And in the middle, we have NC noise, which is just the Gaussian. And on the right-hand side, we have CNC noise, which is just a perturbed version. And you can see it's a little bit fatter than the true data distribution. And the thing to note is that the middle thing looks nothing like the thing on the left, whereas the thing on the right looks much more like the thing on the left. So trying to classify between a data point coming from this distribution versus this distribution is a really easy task, because you'll get some stuff in the middle. Of course, your EBM will quickly learn that data that comes in the middle is not like you can easily. The point is you can easily classify data coming from one distribution versus another, but it's much more difficult to classify data coming from the true distribution and the thing on the right. And by more difficult, the implication of this is that classification is more challenging and training stays informative for longer. Whereas in the first case, by comparison, NC classification is much easier. So your model will quickly learn to classify the noise versus your true samples, and will stop learning because it has learned this task already. Sorry, you want to ask a question?
So my IQ question would be that if you go back, like this whole process, like NC looks a little bit like, with this discriminator idea, looks like a GAN, like a very basic GAN.
Yeah.
So is NC just a GAN?
Yeah, wait for the next slide.
Okay.
Yeah, so but it's a really cool connection. So yes, it does look a lot like a GAN, and in some sense it kind of is. So there's this really cool paper by Yara and Mikhaili. I probably slaughtered the names, but so they view contrastive divergence. They relate contrastive divergence and CNC in an appropriate way, and show that in a sense they are kind of the same thing, just instances of the same algorithm, which is also an example of an adversarial training procedure. So the title of the paper is actually contrastive divergence is an adversarial time reversal game, or something like that. It's a long-winded title, but it illustrates that it's adversarial. So you can relate these three methods, NC, CNC, and CD, under the same framework by observing the following. If you take a gradient of the CNC loss, you get the following expression. So you get a sum over data points where you have a weight, which is 1 minus the classification probability, and a difference. Actually, that should include a nabla. So, sorry, that should be nabla theta on each of these terms. So the intuition about this expression is that this nabla, should have been nabla log p term, encourages high probability near the data. So since xn comes from the data distribution, we're saying that this update rule should give more probability to the data. And the second term, where x prime comes from the contrasted sample, says that you should put low probability on the contrasted samples. And the term 1 minus d downweighs easily classified pairs. So if you use CNCE, then you keep the classification task harder for a longer period of the training procedure, by keeping this classification, like this number to half or longer compared to NCE. And that's exactly what Rich mentioned earlier. So then how can you relate this to contrastive divergence? Well, if we, and again, you should note that the nabla should have been present here. If we let our contrast or perturbation distribution of CNC be a reversible Markov chain with stationary distribution p theta, just as in CD, then the optimal classifier becomes a random guess with probability half of choosing either direction. And under this model, the updated rule becomes identical to CD. Again, you should note that this should include a nabla. And so the high level intuition there to keep is that CD is a version of CNC where you set the perturbation or the reference distribution equal to a Markov chain with the appropriate stationary distribution. And an important detail for making this equivalence work out is that it's necessary to stop gradients flowing through Q theta for the objectives or the update rules to be the same. And stopping gradients is equivalent to ignoring the intractable third term that came in contrastive divergence. Sorry about all the typos as well. This is you can look at the same slide 1,000 times and not realize that you have missing nablas everywhere. So sorry about that. Yeah, so that's an interesting connection. And one last connection between, well, I think we can skip this because we've taken way too much time already. But
We have 15 minutes. So.
oh, we have? Oh, sure. Okay, well, right. I hope we haven't tired people with all those training.
The slides are great, by the way, so there's always typos, don't worry about it. Are you going to talk about the relationship with gas and breakthrough?
Oh yeah, sorry. Yeah, I kind of skipped that over. So I mean, I think okay. So the intuition there that relates actually I guess all of these methods to GANs is that your the adversarial part of the game comes from the fact that your discriminator, your EBM forms a discriminator which tries to classify which pair came from the true data distribution, which one came from the corrupted, if you like, distribution, and you can view you can view the EBM part of it as a sort of the generator which generates those samples. So I kind of again slightly was slightly misleading if I said, yeah, if I led you to believe that I would give a very clear and detailed description of why this is an adversarial game, but
I mean, just to paraphrase what you said again.
Yeah.
So the differences, this might be wrong, but on the fly, the differences are in a GAN, the model you care about eventually, the one you're going to use to simulate data, is the one that you're going to use to generate fake data.
Yeah.
And then you'll use a classifier in a GAN, which is a separate piece of equipment, has nothing to do with the generator to tell the difference between real and fake.
Yeah.
Whereas in the noise contrastive schemes,
yeah,
you're going to use your model distribution, you're going to use to generate data, your generative distribution is going to be in the classifier.
Yeah.
And one of the components of the classifier, and you'll use some other procedure to sample the fake data.
Yeah, and that procedure is in a sense implicitly defined by the EVM. So the procedure for generating the data is part of your the adversarial data, if you like, is part of the
and then the same similarities are they both use a density ratio trick to show that they're correct matches for given the capacity and the right model class for getting the data distribution. So they're very similar in that sense.
So I guess the reason why I was wondering is because, and the other 5 IQ part is because I don't know too much about GANs, but one thing that I have heard many times is that they're quite unstable to train. Because I was wondering if by having the fake data generative process be like nicely fixed to a Gaussian or whatever discrete like kernel density estimate of the true data set is. Like the density ratio trick then with a classifier is stable. Or is MC also unstable?
So okay, I think the first thing to say is that probably I wouldn't use NC, I would probably use CNC.
CNC.
But
CNC,
that's
yeah.
just nomenclature. The full disclosure, I've never used any of these methods to train anything, so I don't know like what people hide under the rugs at home. So I to be honest, I don't think I can give you a grounded answer to that. But it does seem that certain, like, although people report certain difficulties with using some of these methods, like for example CD, it doesn't seem like the problems don't seem to be as acute as with GANs. So GANs are notoriously difficult to train, and I don't know if that's a difference between what people report and what they choose not to report. But it seems that with these methods, it's slightly more, maybe slightly more tractable to do training. That being said, James will talk about an EBM, particular EBM that was by Will Rothel and David Duveneau and et al., in an appendix in the training details, they do highlight that it's not necessarily the most stable way to train models, and they have some issues with it. But I can't quite give you a satisfying grounded answer because I have never used any of these in practice. Cool.
Can I ask a quick question, or do we have to move on?
Yeah, go.
It's kind of the flip side of the question that was just asked, which I guess was like, can you make GANs more stable by kind of fixing the generative process? And my question is kind of the opposite. Can you improve training in these models by kind of having a GAN-like generator, even if what you really care about is the discriminative distribution in these models? Could you still kind of do an online update of the generative model such that you keep this discrimination task hard, which you kind of said in the beginning that, you know, if you have a better generative model that makes this more difficult, then you get better gradient information and then you can train faster. Is there a reason to fix it in the beginning and not kind of optimize that together with the discriminative model?
Right. So in a sense, contrastive divergence does what you said because of this half factor here. So because of the last line, equation 43, the discrimination, the optimal, like the Bayes rule says that distinguishing between these two things is not possible. Like you predict probability a half for both outcomes, and so you keep the training hard for as long as you like, right? So
right.
But still, a problem with this is that basically the length for which you run your Markov chain for might actually need to be quite large.
But could you have some intermediate thing where your generative model isn't fixed, but it's also not a Markov chain, it's some, you know, neural network which you can differentiate through, and then can like, is there some balance to be struck there? Okay, yeah, I mean, I think that's an interesting idea. I don't know. Maybe it is. Yeah, it definitely sounds super interesting and might be worth thinking about more. But yeah, I don't quite have like a mental image of how this could work. But it sounds like, you know, just trying to like draw an equivalence diagram of the various methods and then using like tools from one to improve the other. That sounds like a very sensible thing to try and think about. Cool. Thank you.
I would just add that on our last slide, there's two papers which we didn't have time to either read thoroughly or discuss, that basically one is, you know, directly combining EBMs and GANs and showing that helps GAN training. And the other is a sort of EBM GAN hybrid type thing. So there's definitely some interesting stuff going on in this direction.
Yeah. So the title of the paper is like your GAN is secretly an EBM, right? So yeah, so the connection is definitely there. I'm going to quickly skip over this lecture, this slide, to give James some more time. But another interesting connection is that under an appropriate limit, contrastive divergence is equivalent to score matching, and the conditions are that if you use a Langevin dynamics sampler and you take the step size to 0, or in the limit of the step size going to 0, and you stop gradients flowing through your Langevin sampler, then you get you recover the score matching update rule. So that there's all these methods are fairly intimately connected under some appropriate limits or conditions. Yeah, so now I'm gonna hand over to James to do the final bit on EBM models in practice.
Cool. I'll just very briefly go over, a few cool papers. One of which is this Will Grethel paper that has the appendix, which tells us that doing this training is very hard. But what this paper is basically saying is that, well, every classifier is secretly an energy-based model is the title, so you get the idea. So we could take a standard classifier, defined by some neural network, which outputs logits. We put those through a softmax to get our conditional distribution. Oh man, my slides, I don't know why they're broken. This is terrible. Okay, I'm really sorry about this. Oh well, I guess we didn't really have too much time for that anyway. Fixed slides will be included. The key thing here is that we can treat those logits as unnormalized probability distributions for the joint distribution, and we can marginalize those to get unnormalized probability distributions for the, well, once we normalize those, we can then marginalize them to get the distributions for X. And this lets us do some cool training, which combines the classification training and the EBM training. So we're basically learning the joint distribution of our data X and our labels Y by doing persistent CD, which is a variation of contrastive divergence, where you sort of keep a buffer of your samples that you spent a lot of effort getting with your MCMC, which sort of speeds up training but does make it a bit more unstable. So we train an energy-based model here, and then we train a normal classifier in green, and this ends up giving us a model that's both a good classifier and a good generative model, and good in the sense that the classifier is well calibrated, and the generative model, for example, knows what it doesn't know. It's good at OOD detection, for example. Yes.
Sorry. Again, James, I've been reading through this paper, and it sounds super interesting. So let me just make sure I understand. So again, it's using the density ratio trick. So if you have data from multiple different models, say like class cars versus class flowers, so on and so forth, if we train a classifier with an infinite amount of data, then the optimal thing to do is to take the ratio of the density under the cars cluster versus the flowers cluster, and that's the optimal way to compute the classification probability. Essentially, you do the ratio of one density to all the other densities.
Not quite. So it's not actually using the density ratio trick. The classifier is trained as a normal classifier using standard cross entropy loss.
I understand, but that classifier can then be tied to a generative model.
Yes.
Because of the density ratio trick. It's the density ratio trick the other way around.
Yes, you're right.
Pick off the bits and say that must be proportional to the density.
Exactly. Yes.
But okay, so the thing that slightly worries me about that is, sure, with infinite data, this bit will be the proportional to the density of class 1, and this will be the proportional to class 2, and so on and so forth. But with finite data, that won't be true, and we don't have any guarantees that these normalize for finite data then. So because it might do something funny in the tails, for instance, it might have really high density in regions of space it's not seen before, or not density a value. And so is that a problem then, or are they going to do something to fix that? Do they sort of build in some structure to make sure it does normalize? Because otherwise it might not normalize, and then the sort of unsupervised training costs could do really bad things, because the normalizing constant's infinite. So the problems are all defined again. Yeah,
so they don't do any specific thing to guarantee it normalizes. I mean, so in the absence of enough data, you will have problems there. And they do in fact say, it was hard to tell if the model was learning anything specifically because of the unsupervised part of the training procedure. So this is a problem, and they don't really address it. They say future work, I guess. Yeah. Cool. That was a super brief summary of that. here's another super brief thing, which is that you can combine a VAE and an EBM. And I guess the idea is that VAEs, especially these modern fancy hierarchical VAEs, are quite good at drawing pictures of faces that look really realistic. But what they're not so good at is, again, sort of knowing what they don't know, in the sense that the samples, a VAE can say that something has a high probability, even if it's not from the true data distribution. And so by making a model that's effectively a product of a VAE and an EBM, you can get around that because EBMs are really good at this. They know what they don't know because the training procedure is explicitly like pushing down the energy of things that are in the training distribution and pushing up the energy of things that are not. So the TLDR is that combining these two sort of gives you the best of both worlds. They have a training procedure and they get nice pictures that they posit are likely to be from the true data distribution. A final neat example that sort of ties into these ideas is that, okay, I've been telling you that energy-based models are good at OOD detection. And so, this paper explicitly uses this and use it in two ways, both as like a post hoc thing. So taking a pre-trained model, using what they call an energy score and using that for OOD detection, rather than something like the maximum softmax probability or other things that are commonly used on pre-trained classifiers. And they also come up with a clever little energy-based loss, which improves the sort of OOD detection capabilities of a model. And for example, that ends up outperforming the joint energy-based model from Grathwohl et al. But yeah, Stratis, do you want to jump up here and we can just wrap up? Yeah, sorry for going through those last ones in huge haste, but if you're interested, you can check out the paper or papers. And then Stratis, do you want to?
Yeah, so I guess in conclusion, we've seen generally EBMs are flexible class models, which would expand the toolbox, the modeling toolbox that we have. They're not constrained to be analytically tractable in terms of the normalization constant. So it will be interesting to know how to train them. And so there are several approaches for training EBMs, each with pros and cons. We've seen contrastive divergence, which makes training tractable, although it comes with a cost in, as James mentioned, in stability, and also potentially still needing to run a Markov chain for a fairly long time. We've seen score matching, denoising score matching, and sliced score matching, and each of them again come with pros and cons. So score matching came with a large computational cost, and then denoising SM gets around that, but introduces the variant, sort of this variance trade-off that the smaller the variance is, well, the smaller the noise is, the larger the variance of the estimator is, and the larger the noise is, the thing you learn is further away from the true data distribution. Slice score matching, again, Rich pointed out that to get good coverage in terms of these V vectors that you use to do the slicing, you might need quite a lot of them, or you might need to be smarter about how you generate them, which is a non-trivial task. We saw noise contrast estimation and conditional noise contrast estimation, which also come with their own trade-offs. NC we saw can become quite easy, like the classification task can become really easy really quickly. And conditional NC solves some of the problems, but itself is not perfect either. So and we also saw some of these are equivalent under certain conditions. And in summary, this is a table adapted from Grathwohl et al, which summarizes sort of benefits or the various features of the different approaches. So in conclusion,
energy-based models are great. Well, they could be great if we could train them easily, but they've got lots of promise, I think. Good at OOD detection, for example, let us be fairly flexible, if not infinitely flexible, with well, not infinitely flexible, to be clear, with the sort of neural network architecture we use, for example. So there's lots of interesting stuff going on here. There are also many things we didn't get to talk about. There's many other ways of training these models, various generalizations of CD and SM that minimize differences between KL divergences. There's methods that use standard discrepancy, including this cutely named LSD method. There's various forms of adversarial training. As you can imagine, we sort of saw those themes coming up. There's also a whole bunch of other cool EBM papers we didn't get to talk about, including these two GAN flavored ones that I briefly mentioned earlier. And the sort of the holy grail of papers, if you want to go and read more on sort of the main training methods we talked about today, is this sort of review paper from Song and Kingma, which has many more details that we didn't get to talk about. So I think that's everything we have, right?
Yeah.
So thanks everyone for attending, for asking questions and all of that. Thank you. Any good references? But yeah, we'll send through some fixed slides so that you can look at all the details in your own time.